Hello everyone, and welcome to the very first online lecture of probabilistic machine learning at the University of Tübingen. I'm not going to lose any time with introductions, but instead I'll start the course right away with an experiment that I've inherited, and by extension you are now inheriting it from the late and great David Mackay. So what I have here is, of course I have it in the bag, 3 cards . One of which is red on either side. That's the first card. One of which is white on either side. That's the second card or third card. And one of them is red on one side and white on the other side. And what I'm going to do now is I'm going to put these cards into a nice little bag like this, shake the thing around a little bit so we don't know anymore which card is where, and then I'm going to randomly grab into it and just pull out one card, and I'll put this down onto my notebook, and now you can see that the side of the card you can see is red. And the question for you is, what's the probability, given that you see this red card, that the other side of this card, which you currently can't see, is also red? Normally, I would tell you to talk a little bit with your neighbor and discuss this, but because this is a video recording, you can just stop the recording for a moment, and once you've come to a conclusion, have an idea, you can switch it on again. Now that you've done so, I can provide you with a few alternatives, possible answers. Maybe your answer is the probability for the other side of this card to also be red is 1/2, because what's it going to be? It's either white or red. Maybe your answer is the probability for the other side of the card to be also red, is 2/3. Or maybe it's something completely different because you have your own theory. Now, a non-formal, non-mathematical way to answer this question is that the correct answer is actually 2/3, and that is truly the correct answer. Why? Well, because there are 3 red sides of cards involved in this problem, and I've just randomly picked one of them because you don't know the orientation of these cards, and of these 3 red cards, 2 of them have red on the other side and only one has white on the other side. Now, in fact, if I actually turn this card around, you can see that it's white, but of course that doesn't invalidate this particular point. This kind of question I've just asked you is an extremely elementary form, maybe it's the most reduced possible case, of something that we call an inference problem. An inference problem is a question that one can ask for which, given the information at hand, there is no true correct answer or no answer that can be given with certainty. So therefore, it requires an answer with uncertainty. And these kind of inference questions, this particular one might have sounded a little bit contrived, but it was actually, it was deliberately constructed to be as transparent as possible. All the rules are available. There is no trickery involved. I did not play around with these cards inside of the bag without you noticing. And yet, there is still a notion of uncertainty in the end, even though you were aware of all of the rules. These kind of questions, they don't just apply to cards in bags. They are actually the typical, most prominent question that we face in our daily lives. When you go outside, if you're allowed to, and have a look at the sky, then typically you'll be able to predict with a relatively high certainty for a few minutes or hours into the future what kind of weather you're going to be facing if you go outside by looking at the sky. That's a simple kind of inference problem that we face in our daily lives, because it's clearly impossible to predict with high certainty what the weather is going to be, but it's possible to do so with a certain degree of imprecision. That's a simple example, but many, particularly hard tasks that humans deal with professionally are also associated with this notion of uncertainty, and often it's actually the kind of jobs that we associate with particularly high human intelligence. When a judge decides, or over the course of course proceedings, tries to decide whether a defendant is guilty or not, then she's usually never able to take this decision with perfect certainty. Of course, because she wasn't at the scene of the crime. She can only collect evidence later on, which over time might accumulate to remove so much uncertainty from the process that the judge is then able to decide with high certainty, with low uncertainty, whether the defendant is guilty or not, and only then, by law, is she allowed to actually pass judgment. When scientists try to decipher the way the world works, then it's almost always impossible to build one experiment that perfectly captures all information necessary to unravel a rule of nature, to perfectly understand a particular process. But instead, scientists try to devise experiments that collect individual pieces of evidence, which, taken together, then form an increasingly certain picture of the world. And when a doctor, maybe that's the best example in these trying times, when a doctor is faced with a patient that exhibits certain symptoms, then of course no medical doctor is able to say with certainty, with a logical kind of certainty as we are used to from computers, whether a patient has a certain disease or not, and how they are going to respond to treatment. But instead, medics have access to various diagnostic tools, from just looking at the patient up to high modern precision medicine techniques to collect evidence about what kind of ailment the patient has, and also to predict into the future what the reaction is going to be to a particular treatment. Now, clearly, this is an ability, reasoning under uncertainty, that we would like to have for ourselves, and that maybe we want our computers, our machines, to replicate as well. However, classically, a computer does not actually allow us, at least not out of the box, to do this kind of uncertain reasoning. The kind of formalism that you learn in an undergraduate computer science or computer science computational logic course is propositional logic, which allows to map true statements into other true statements. The important point being that there is only two binary values of truth, false and true. So, for example, imagine that we have two variables which might be called A, and variable A stands for it is raining outside, and variable B stands for the street is wet. Then a classic formal logic allows us to devise statements like this one, this string, which is spelled out as from A follows B, and which is represented by this truth table, which says that if A is true, then B also has to be true. So if it rains, then the street is wet. And it allows us also, so this process of reasoning that if A is true, then B also has to be true is classically called modus ponens. But it also allows actually in a very specific sense, inverse kind of reasoning, which is that if B is false, then A also has to be false. So if you look outside and you notice that the street is dry, then this implies that it cannot have rained recently. However, propositional logic does not allow us to make the other two kind of, or reason about the other two kind of possible combinations of true and false. Even though these are conclusions that you might make yourself with your human brain. So if you look outside and you see that it's not raining, so A is false, then you might infer that it's quite likely that the street is dry. So B is false. But propositional logic doesn't allow us to make this kind of statement. Why? Well, it does that with good reason, because there might be another explanation for the street being wet. So let's say there is someone outside, a gardener with a hose, who is spritzing water onto the street, so the street ends up being wet anyway, even though it's not rained. The fourth possible solution also doesn't work. So let's say you're looking outside and you see that the street is wet. Then typically you might be willing to conclude that therefore it has rained, but that also doesn't work because someone else might have gone outside and wetted the street with some water that didn't come from the sky, and therefore you've drawn a wrong conclusion. So why does this not work in classic propositional logic? Well, the reason for this is that it's not the formalism itself, it's that it is restricted to binary truth values, that it's only possible to say something is true or false. So to remedy this problem, which is evidently an important practical problem, we need to have a formalism which extends binary truth values or interpolates from binary truth values to something in between, to a statement that is partly true, that is perhaps true, that is probably true. So we would like to be able to create this kind of plausible reasoning. We want to be able to say that if A is true, then maybe B becomes true, or at the very least it becomes more plausible. Or if B is false, then A either becomes false or at least it becomes less plausible. And if B is true, so that's something that classical logic doesn't allow us to reason about, then we might want to be able to say something like A becomes more plausible. If the street is wet, it seems to become more plausible that it has rained. We're never quite certain, but we become more certain that it might have rained. And finally, if A is false, so if it's not raining, then B becomes less plausible. So it's less likely that the street is wet. There are potential explanations left, but we deem them relatively unlikely. We would like to be able to write this with a notation that looks a little bit like this. So we're going to read this out, and in a moment I'm going to introduce this more formally, as the probability for the statement B, given that A is true. And this is going to be the probability for the statement B to be true. So a statement like this might replace this string by, instead of saying if A is true, then B is true, instead saying if we observe A to be true, then B becomes more plausible than if we do not observe A to be true. This is the kind of extension we want to make, and we have to do so because everyday reasoning requires us to be able to make these kind of statements. A perhaps nicer way to put this is in this quote by James Maxwell, one of the most seminal physicists of the 19th century, who said that the actual science of logic, so propositional logic, is conversant at present only with things either certain, impossible, or entirely doubtful. So either true or false. None of which, fortunately, we have to reason on, because this is not the situation we actually face in real life, because life is never certain or impossible. Therefore, the true logic for this world is the calculus of probabilities, a notion of uncertainty, which takes account of the magnitude of the probability which is or ought to be in a reasonable man's mind. So if you are a reasonable human being, then I hope that you're interested in this notion of uncertainty, and therefore in this course, because that's what we're going to be doing in this course. We will first establish a formal mathematical framework, and we'll actually do that today in this lecture for a probable reasoning. Then, over the course of the entire remaining term, use this to build a powerful collection of mechanisms that apply to real-world problems. And in doing so, we will encounter many mathematical and computational challenges which have to be addressed by specific technical tools. So a large part of this course will be dealing with designing these algorithms and models and tools to get this inference actually off the ground and apply it to more than trivial problems like cards in a bag. we're going to start right away with defining this formal process. But maybe at this point and over the course of the term, there will be typically in every lecture maybe 3 or 4 of these gray slides. That signifies an opportunity for you to stop the video, because this is sort of an end of a train of thought. Maybe get up and get a glass of water or walk around a little bit to collect your mind. And then once you think you've understood this part, move on to the next one. Okay, now it's time to construct our formal system of reasoning using probabilities. And before I write down some axioms, let's look at an example that maybe gives an intuition for what we actually need. And that example is a roulette game. So I'm sure everyone knows how roulette works. There is a wheel of numbers that rotates, and someone throws a ball around those numbers until blink, it falls into one of these boxes. And next to the wheel, so notice that nobody actually interacts with the wheel other than the croupier. So there is the players can watch the wheel, but the game actually takes place on this board which is next to it. And this board lists all of the numbers on the wheel, but also a bunch of derived statements or variables. Like, for example, whether the number that we've seen is painted in red or black on the wheel, whether it's even or odd, whether it's in the top or the bottom half of the table, or even whether it's in the top, middle, or lower 12, so 1/3 of the entire set of numbers. And players are actually allowed to construct combinations of these statements. So they might put, because they have more than one chip, they might put a chip actually at the intersection of numbers, or even at 4 corner intersections, but also they might both bet on even and a certain number, for example. So imagine you are the designer of the roulette game, and your job is to construct a set of rules for this game such that it's fair. Now, how is this connected to our notion of probability? Remember, what we want to construct is a set of reasoning rules which do not use an indivisible chunk of true or false that we have to assign in a binary fashion to one particular statement, but instead to take this chunk of probability and distribute it across possible statements, such that some statements can be more or less likely. So here, what we need to construct is we first need to think about this wheel. So the wheel is some kind of mechanism that produces outcomes, elementary outcomes. In this case, there are 37 of these possible outcomes, 36 numbers and a 0. And then we are not going to make statements. So the players don't actually make statements about those numbers necessarily, but they make statements about these derived quantities. So the individual numbers are actually part of these possible statements, but there are also derived statements that are essentially collections of subsets of the numbers. So for example, the red subset is the subset that is marked in red on this board. And what we now need to make a fair game is, as a third kind of quantity, the first object we have to think about is the wheel. The second thing we have to think about is the table and how to lay it out. And the third thing we have to think about is the rules of the game, which allow or which ensure that the payout is fair. And now we have to think about what it actually means for the payout to be fair. We're now going to turn these statements, or this sort of intuition, into a mathematical formalism of axioms. And these axioms go back to a wonderful Russian mathematician, by all accounts a very interesting man, called Andrei Nikolaevich Kolmogorov. He was born in the 1903 in the early 20th century and lived until 1987, and he clearly had a very interesting life. He was born to a mother who died at birth. His father didn't care for him. He was raised by his aunt, who also afforded him a good mathematical education. There are all sorts of interesting stories connected to his name, and over the course of his life, he became the father of modern probability theory. He wrote a book in 1930, which I have here. It's actually a very nice book. I recommend it. It's very thin, as you can see. It's written in German. There's also an English translation. It was published in German and written by Kolmogorov in German, published by Springer in 1933, which is why it's not so easy to Google for it, because Springer doesn't advertise books that it published before 1945. But I recommend that you have a look if you read German or look at the English version, because it really is a wonderful text. It's very precise, very short. It's almost like a paper, and essentially raises all of the issues that we have with probability theory to this day and discusses them very well. And so Kolmogorov provides one way of constructing a probability theory, which I prefer because it is purely mathematical. It's extremely intuitive. There are other motivations for probability theory. One, for example, is connected with the American physicist Richard Cox, which is more philosophically motivated, so motivated from a notion of common sense. The advantage of Kolmogorov's formulation is that it's very precise and clean. A disadvantage is that there is one key aspect of probability theory, which I'll mention in a moment, which actually has to be defined by Kolmogorov rather than derived by people like Cox. So how does Kolmogorov's system work? So remember our example of the roulette board. We needed three pieces. We needed the wheel, the table, and the rule book, how the payout works, right? The rules of payout. So Kolmogorov defines all three of these. And I'm going to show you the original text for a moment, which is in German. So this is actually copied from, literally I copied this from page 2 of the book. And then we will construct from, I will read it out in English, don't worry about it. And then I will construct from that a slide with a modern version of these axioms. And if you want to follow along really precisely, if you've already seen this before, then you can check what the minor differences are between the classic formulation by Kolmogorov and our more modern one. So let's start with the wheel, our roulette wheel. That's the set of elementary operations. So Kolmogorov says we need this object, which we will call E. E is a set of elements, psi and eta and theta and so on, which we will call elementary events. That's the roulette wheel. Now we need the roulette board. For that, we define this German calligraphic F, which is a set of subsets of E. And these elements of this set of subsets will be called random events. And we require from this set of subsets that it fulfills the following three axioms. The first one is that it's what Kolmogorov calls a Mengenkörper, so a field of sets. And if you don't know what that is, he actually handily provides the definition in a footnote by just referring to Hausdorff, who says as a system of sets is called a field if both the sum and the intersection and the difference between two sets in the system are part of the system. So this is analogous to the notion of a field and Körper in algebra, where you need an operation which has the property. So here the operations are in classic algebraic fields, the operations are called plus and times. Here the operations are called intersection and union and difference, and they have the property that if we apply them to elements of this field, then we stay within the field. That's the first axiom we need. The second axiom is that our set of random events has to contain all the atomic events. So our roulette board has to contain all the individual numbers on it. And thirdly, now, actually these are the two axioms we need for this set of sets. And so this is basically the definition of our roulette board. So what we've basically done by this is set out a set of rules which says that our roulette players are allowed to place any bet by combining arbitrary elements that are already on the board. For example, they can construct a set of all red numbers and call it the set of all red numbers. and they can define the set of the upper 12 numbers. And then they can define the set of the upper 12 of the red numbers within the upper 12 numbers. That's an intersection, right? Okay, and so now we need the third part. The third part is the rule book. And so for the rule book, we will need to come up with a way of assigning probability to the atomic events. So for that, we will distribute truth, and we will distribute a finite amount of truth, 1, across the atomic events, and then come up with a rule for how those probabilities on the atomic events translate into probabilities on the derived events, which are part of this set of possible events, set of sets. The rules for that, which Kolmogorov sets out, are that for every element, for every set in F, we will define a non-negative real number. So that's what we will call the probability. And we will call this the probability. It's a function that maps from A to a real number, a positive real number. It's called P of A, the probability of A. We will call this the probability of the event A, and it requires that the probability of the entire set, the collection of all atomic events, is 1. So that's what I meant by taking the block chunk of length 1 and distributing it across all of the events. And if we have two disjunct events, like for example, or the number 0 and the number 12, then it has to hold that the probability of the sum of these two events, so the probability of either A or 12, either 0 or 12, has to be the sum of the individual probabilities. And of course, that is going to be the mechanism by which we ensure that all of our derived events have meaningful probabilities. Such a system of sets with this function P, if it fulfills these 5 axioms, Kolmogorov says, we will call a Wahrscheinlichkeitsfeld, a field of probabilities. Now, if you don't like reading this in German, I'll now do this again in English. And so the reason I'm going to do this twice is that people often get introductions. So if you're not a particularly mathematically inclined person, then you might find the modern definition of probability theory a little bit cumbersome or difficult to understand. So if I would have just thrown this definition onto you, you might have found it quite hard to understand. I hope that this way of getting to the rules has motivated a little bit better the somewhat weirdly named modern mathematical concepts that are now going to follow. So here's how we would do this in modern English mathematics. It's essentially the same thing, but there's going to be a very subtle difference that we will notice in a moment. So we will first define our wheel and our roulette board, and let's think about the rules, our probabilities, later. To do that, we actually do not use any notion of probability theory. We're just using the theory of sets. And so you can call that set theory if you want. It's also called measure theory. So if we first start with our wheel. The wheel is again called E. It's the space of elementary events. And now let's consider, and for this definition, the power set of E. So that's the set of all subsets of E. And consider a subset of that power set. We call this Fraktur F. These events are called random events. So far, so good. That's exactly the same as for Kolmogorov. If F satisfies the following properties, we will call it not a field of sets anymore, but, somewhat annoyingly, this very cryptic name, a sigma algebra. A sigma algebra is this collection of sets such that the elementary events are all in the set. That's for Kolmogorov axiom number 2. For us, it's axiom number 1. If we have two sets from F, then F is closed under their difference and countable unions and countable intersections of these sets. So the difference to Kolmogorov's definition here is actually the infinity up here, that we allow countable but unbounded unions and infinities and intersections. That's why this is called sigma algebra and not a field of sets, if you like. but it's really just, at least at first sight, a minor difference, and it requires a little bit of fixing later on. So that's just a sort of a post hoc correction that later generations of mathematicians have made to Kolmogorov's axioms to make them a bit easier to use. We will notice in the next lecture why this is actually important. This kind of property already implies that the empty set is actually a part of F. This follows from the third axiom. If, by the way, it's also true that for countable atomic events, E, we can actually, you can think of the sigma algebra as just a power set. The power set has this property. This is not true for uncountable spaces, and we will have to think about that in lecture 3, but we will talk about that when we come to it, because it's actually a little bit of a tricky bridge to cross. If F is a sigma algebra, then we call its elements measurable sets, and the space that is created by considering the atomic events and all the possible subsets you can construct on it within the sigma algebra is called a measurable space or a Borel space. Notice that so far I haven't defined probabilities at all. These entire parts are just statements about what we will consider an acceptable set and set of sets. What's admissible to talk about? What are the ways in which players are allowed to place their bets on the roulette board to construct a permissible bet? Now we have to talk about the payout rules. How do we actually construct probabilities for individual events? By the way, if you're wondering why I talk about payout rules and probabilities almost interchangeably, think about what the inverse of a probability is. Okay? Good. So this was our definition of the roulette wheel and the table. Now comes the definition of the rule book, the probabilities. So let's take a measurable space, so a Borel space, and we will define this function p, which we will call the probability of an event. Kolmogorov even has an axiom for the fact that this thing exists and that it maps to the positive reals, not the negative numbers. This is called a measure. It's not yet a probability. It's just a measure if the probability or the measure of the empty set is 0, and for any countable sequence, so that's a sequence of elements of the sigma algebra which are pairwise disjoint so that they do not overlap or intersect. We require that, and this is really the sort of master axiom for probability theory, not the master theorem, but the master axiom, that the probability of a countable union of these disjoint sets is equal to the sum over the probabilities of the individual sets. So this is a very natural definition. It just says, imagine you have two separate possible events. So on the roulette board, this might be the top 12 numbers and the bottom 12 numbers. And we have assigned probability to both of these events. And the probability of the OR of these two, so the joint of them, has to be equal to the sum of their probabilities. Why? Because otherwise we could construct what's called a Dutch book. So we could construct a strategy to bet which guarantees that we will win. So this is the definition of a measure. And now there's a final additional add-on, which is the only distinction between measure theory and probability theory is a single line which says such a measure is called a probability measure if the probability of the joint of all atomic events is 1. So all that says is that there is no infinite truth in the world. There's only a finite amount of truth. A statement is either true or it's partially true, but it's never more than true. Okay, that's actually really straightforward. And that in itself is the entirety we need to move from set theory to probability theory. Why is this important? It's important because most people agree with set theory, but there are many people who disagree with probability theory. So if you disagree with probability theory, either you have to disagree with set theory for countable and even finite sets, or you have to disagree with that one line, that there is only, that a statement cannot be more than true. I challenge you to do one of them and not feel stupid in doing so. Why is this a great formalism? Well, as everywhere in mathematics, once you've written down a set of axioms, you want to put them to use, by actually deriving something from them. And Kolmogorov does that immediately, actually on page 4 or 5 or so of his book. He starts showing interesting properties. So first of all, there is a wonderful result that is called the sum rule. I'll just state it and then I'll tell you why it's useful. So the sum rule is a very simple observation. Notice that the entirety of the atomic events, E, can be written as the sum of any element of the sigma algebra, any A, and its complement, of course. That's really just a definition of the complement, right? That's not even an axiom, it's just a definition. Now, therefore, we can write the probability of E, which is 1 by definition of axiom 4, using sigma additivity, 5, to get that 1 is equal to P of A plus P of the complement of A. So therefore, the probability for an event A is 1 minus the probability of its complement. Okay? That's, if you like, the law of inverse probability. No, sorry, not of inverse probability, of complementary probability. Now, now we're going to make a definition. So we'll just introduce a new notation. We will talk about the joint probability, P of E, A, and B, as a shorthand for the probability of the intersection of A and B. This notation will be much more convenient later on when these A's and B's are not always sets anymore, but we will adapt the notation a little bit. So this joint probability, we can make a statement for that by noting that any A is equal to, and this is again just set theory, A is equal to the intersection of A and E can be written as B and non-B, or B and the complement of B. So therefore, using sigma additivity, P of A is equal to P of A and B plus P of A and the complement of B. So the probability for A is the probability for A. So how can we describe A? Well, we can describe A in terms of the part that intersects with B and the part that doesn't intersect with B, right? That's pretty straightforward, but we're going to use this sum rule very extensively in probability theory to, for the operation of getting rid of one variable. So what this rule says is if you have two variables in your reasoning system, A and B, and you'd like to get rid of B because you don't know anything about B, you're just uncertain about it, then this rule tells us how. We just sum out the possible values of A. The second statement we'd like to make is, unfortunately, this is the point where Kolmogorov, with his strong mathematical bent, has to actually define something rather than derive it from common sense, is a definition rather than a theorem. So it's a definition for what's called the conditional probability. Conditional probabilities will be written like this, and we will call them, we will read this line as the probability for B given A. That's how you write this line, which is defined as assuming that A has a probability larger than 0 as the probability of A and B divided by the probability of A. How should we think about this? Well, follow me along. If you think of the entirety of E as the circle, then we can draw a nice little Venn diagram. So let's say this is B and this is A. Then P of then the function P, the probability, assigns a probability of 1 to this entire circle, and it assigns a certain amount of probability to B. Now to construct, and to A of course. Now we assume that the entire probability in this circle is larger than 0, and we can construct a new probability on just this domain by computing the probability of this subdomain and dividing it by the probability for A. Now, why is this interesting? It's interesting because, and you can easily show this yourself, I'll leave it to you as a very simple finger exercise, it's really just plugging in definitions. You can show that the probability for B given A, this conditional probability, is always larger or equal than 0. So this is the axiom 3 for probabilities of Kolmogorov. So it's just they are a map that maps to positive, non-negative real numbers. it's easy to show that the probability of E given A is 1. You literally just plug in the definition of E in up here. And for disjoint sets, we also have sigma additivity. So therefore, this function actually is itself a probability. That's useful because it allows us to move to restricted probabilities. So if you know that we are within A, this operation provides a new probability within the domain of A. And what are we going to use this for in reasoning? Well, we'll use it to reason about one variable given the other. So if you have information that comes from variable, like you want to say something about B, but you've made an observation about A, then this rule tells you how to incorporate this in your reasoning process. We're almost done, though we're not quite done yet, because there is this P of A down here, and that's kind of often a problem to construct, so we have to say what this actually means. And for that, we use what's called the law of total probability, which is actually an extension, if you like, of the sum rule. So if we, again, consider a set of these pairwise disjoint events A, so that they do not overlap, also assume that together they span the entirety of E. So this could be, for example, A1, A2, and the complement of A1 and A2 in E. Then for any element of the sigma algebra, for any event X, the probability for X can be written as, sort of it can be sort of represented in a, almost in like a basis for X, or sorry, not as basis, a generating set for X, as a sum over conditional probability times probability. So probability for X given AI times P of AI. Why is that? Well, so here's the entire proof. We just noticed that any X can be written as the intersection between X and the entire space, and then use the definition that we have up here, or our assumptions about this set of disjoint sets, to reconstruct E by the elements of A, and then use sigma additivity, 5, our rule book for how uncertainty arises, or how probabilities add up, to notice that this property is basically true, right? So we just apply the definition of the conditional probability and sigma additivity, and that's it. So why is this a useful, what are we going to use this law of total probability for? Well, we are going to use it to complete the construction of the conditional probability into a wonderful theorem that provides the basis for all inference processes using probabilities, and that is called Bayes' theorem, which states that the probability for AI given X is the probability for AI times the probability for X given AI, divided by the sum over all such terms over I. This should be a J. I'm sorry, I'll correct that in the slides. There should be a J here, of course. So, or another summation index. So, how do we get to that? Well, the proof is straightforward. It's just a definition of the conditional probability and plugging in the law of total probability. This Bayes' theorem provides the basis of all probabilistic reasoning, but I'll tell you more about that after the break. First, I'll show you a summary of what we just did. These axioms I just wrote down, which are actually, if you think about them, hopefully very easy to buy, because they're really just set theory with a measure on sets, and the only constraint that makes that measure into a probability is that there is only a finite amount of truth. That's it. So there's not much to question about that. If you do so, then you can directly derive these wonderful theorems, which are the sum rule, which is a way of getting rid of variables in your reasoning problem, the product rule, and directly arising from the product rule and essentially the sum rule, which is restated as the law of total probability, Bayes' theorem, which, so here in this case, you can even use it directly from the sum rule, right? Which is a mechanism for making statements about one variable, given that you've seen some other variable, that you have some other piece of information where we are within this Venn diagram. And in a moment, I'll give names to these individual terms, and then we'll talk about how we can use them to do something interesting. But for now, you should take again a brief break, stop the video, think about what we've just done, and then let's come back and continue. All right. Now that we've introduced this formal mechanism of reasoning under uncertainty, of distributing knowledge across several possible explanations, we can spend the rest of this first lecture getting a bit of a feel for how this mechanism works and appreciating its strengths, and also finding a few challenges that we will have to deal with over the course of the rest of this semester. To begin with that, I'd first want to there we go. I first want to give a few philosophical interpretations for these terms in Bayes' theorem, the ones that many of you will have heard about before. So the way I introduced this framework so far didn't require me to give philosophical interpretations for the terms that show up in these expressions that we've been looking at. But of course, historically, this framework is much older, actually. It's much older than Kolmogorov's measure theoretic formulation. And the terms in Bayes' theorem have always been associated and immediately been assigned philosophical interpretations. So this is not going to be a bit of a big surprise for most of you. So let me just move the mouse out of the way. So this probability for a hypothesis X given the data D has always been interpreted as a posterior distribution, and in fact you've already noticed me using words like data. So let's say we have two different statements, an observation and a latent quantity X, data and latent quantity, something you see and something you want to reason about. Then this conditional distribution for the thing you'd like to know, given the stuff you got to see, is called a posterior probability. And it arises by Bayes' theorem by multiplying P of X with P of D given X, the conditional, and dividing by the probability for D, which can be written as a sum by the law of total probability, as a sum over all possible values that X can have. So all possible elementary events, if you like, or also elements of the sigma algebra that together make up, that are mutually distinct and together make up X by summing out over all of these possible X's. So this term up here, P of X, is usually called the prior probability. P of D given X is called the likelihood for X. Notice that it is, when we use the word likelihood, we talk about a function of X. P of D given X is a probability for D given X. It's not a probability for X, but it's treated as a function of X. And the word likelihood has been specifically reserved for this kind of use. And this denominator, P of D, which can also be written over as the sum, is known as the evidence for the observation D. It's how likely this observation D is under any possible explanation for how it might have come about. Under this interpretation, we can think of Bayes' theorem as weighing, as computing a posterior distribution for X given the data by weighing the individual possible explanations for the data and the underlying hypotheses relative to each other. So how likely is it that X is the correct explanation for the data? Well, for that we have to reason first about how likely X is in itself, and then multiply with the probability to observe the data if X is indeed the correct explanation, and then normalize this probability distribution, because that's how we define conditional distributions, as a normalized probability, by normalizing by the sum of all such possible explanations for the hypothesis X, by summing out over these individual terms. Many of you have heard these terms before, and we're going to talk about them many and many times over the course of this semester, so I'm not going to dwell too much on this. One key point to keep in mind here is, and I will get back to that later, is that as we just derived this framework, you might have noticed that the entire, like the key contribution, the key part of the construction was the construction of the sigma algebra and the probability measure P. All of these together form the set of assumptions that we use when we do probabilistic reasoning. It's not just the prior distribution. And to give you a feeling for that, I'd now like to go through a few example applications and problems and questions to see how we use Bayes' theorem in practice. And let's start with this very simple example that I did at the beginning of this lecture, showing you 3 different cards, one of which was red on either side, one of which was red and white, and the final one was white on both sides. And the question was, what's the probability, given that you see a red side, that the other side is also red? I gave a simple explanation for how you could do this in sort of an informal way. You could notice that there are there are 3 red sides, and 2 of them have red on the other side, so the probability must be something like 2/3. Let's see whether Bayes' theorem reconstructs this result. To do so, we have to do a little bit introduce a little bit of nomenclature. So we're going to define a variable which we call card, the identity of the card. There are 3 of these cards. Let's call them 1, 2, and 3. Card number 1 is the one with 2 reds. Card number 2 is the one with red and white. And card number 3 is the one with white on both sides. And there is another variable called color, which takes 2 possible values, not 3. It's either white or red. Now we can write down a conditional posterior distribution or conditional posterior probability for the individual cards, 1, 2, 3, given that we've observed color red, and we can just apply Bayes' theorem. So this posterior is the prior times the likelihood divided by the evidence. So what are these terms? Well, first we have to think about the prior probability, and when people critically talk about probability theory, they often bring up the prior distribution, the prior probability as a key issue, a key philosophical problem. But in this case, I hope that most of you will agree with me that the prior is actually totally unproblematic. I just picked any card out of the bag. And if you believe me that this is actually what I did, that I didn't cheat in doing so, then of course the prior probability should be, think of it for yourself, 1/3, right? Because there are 3 cards. So the prior is very easy here. The more interesting object is actually the likelihood. What's the probability to observe the color red given that we have card 1, 2, or 3? Well, so for the first card, this likelihood is evidently 1, that I will write down this number here, because there is no other possibility than to see red. For the second card, the likelihood is 1/2, and for the third card, it's actually 0, because if it's the white card, there's no way I'm going to see red. So this is the only source of structure that enters this problem. The prior is totally uniform. So what's the evidence, the normalization constant? Well, this is also easy. It's 1/3 times, because that number can get out of the sum, times the sum over 1 plus 1/2, 1 plus 0. So that's 3/2 times 1/3, which is 1/2. The prior is the same for every possible card. So these 2 numbers together give 2/3. And the only thing that changes from one scenario to the other, from one hypothesis to the other, is this likelihood, which is either 1 or 1/2 and 0. So the question I asked at the beginning of this lecture is, what's the probability, given that you see red, that the other side is also red? In our namespace here, where cards are numbered from 1, 2 to 3, that question essentially is, what's the probability for card 1? Because that's the one that has red on the other side. And we can now see, if we take this likelihood and plug it in here, we get exactly 2/3, which is what we wanted to see. Another thing you might notice is that the probability for the other card, for the one with white and red, is 1/2 times 2/3, which is 1/3, and 2/3 plus 1/3 is 1, which is something our mechanism requires us to have, that the total sum of our probabilities remains 1. And in fact, of course, this only works because the third card has probability 0, which it has been assigned to by the likelihood. Here's a pictorial view of this. Maybe this helps for some people. You could give names to these individual variables, call them card and color. Now we get to see the color. We assign a prior probability to all 3 cards. That probability I've set it to be uniform. Of course, I don't have to do this. There's no mathematical reason I have to do that. I could distribute truth in a different way. But our assumption, and I hope you believe me that this is a good assumption, was that we draw cards with equal probability from the bag. Then we multiply by the likelihood. The likelihood is either 1 if I take the red card to see the red side, 1/2 if I take the red-white side, or the 0 for white, and then I divide by the evidence. The evidence is 1/2, so dividing by 1/2 is like multiplying by 2, and this gives us our posterior distribution. The next example we should talk about is the observation that I made at the beginning, actually sort of after the first few minutes of this lecture, that propositional logic is too limited to represent everyday reasoning under uncertainty. So just to remind you, I made this example of 2 variables. It's raining outside and the street has become wet. So B being the street is wet. Classic propositional logic allows us to say if it rains, then the street gets wet, and if the street is dry, it can't possibly have rained. What we'd like to do is to extend this to include statements like, so first of all, to weaken statement like this, so to be able to say if it rains, the street becomes more likely to be wet, or if the street is dry, it becomes less likely that it has rained, but also to do to add the 2 kind of inverse reasoning processes that are not possible under propositional logic, which are that if the street is wet, it becomes more plausible that it has rained, or if it hasn't rained, it becomes less plausible that the street is wet. It's actually possible to show that this is the case very simply by plugging in real numbers into Bayes' theorem and just checking that inequalities hold. I'm not going to do this here because it's actually one of your homeworks. We're going to talk at the end of this recording very briefly about how homework exercises work for this lecture, and then there will be more discussion of that in our first inverted classroom on Tuesday, the 21st of April. Instead of spending too much time with this example then, I would like to show you something else and give you a concrete and quite recent example of why it's useful to know about probability and why reasoning under uncertainty is often not as intuitive as people think. And to do so, let me see if I can briefly do this here. I want to use an example that actually happened or is happening in real time just now. So about a week ago, I think on the 6th of April, the US Food and Drug Administration, the federal FDA, provided an emergency permission to a company called Celex to introduce to the market an antibody test for the coronavirus disease COVID-19. Antibody tests are different from virus tests. So this is a test that checks whether it can detect in your bloodstream immune responses to the coronavirus, specific to the coronavirus, which are an indicator that you've probably gone through the infection and indicate that it's likely that you're now immune to this disease. This test looks, you can see a little drawing here. So this, by the way, this document I've opened here is actually the official sort of tech sheet, essentially spec sheet for this test provided by the company that built it. This device it's a use at home device, if you like. It looks a little bit like a pregnancy test. You put a drop of blood that comes from a pinprick onto this part of the device, and then over time, up to 3 of these test strips become red. And if they're all red, then that means that the test has detected some antibodies in your blood. This test has gone through the news because, in particular, because the British government has announced that they are ordering a very large number of these tests, as far as I know, about 3 million of these tests, to distribute by mail to the British public so that people can test at home whether they have gone through this coronavirus disease, because, of course, people are a bit unsure whether they've actually had the disease or not, because there are all these rumors or also evidences for asymptomatic courses of the disease, so people are actually often unsure whether they've had it or not. So if you look closer into this document, then one of the numbers you can find, an interesting bit, is over here. There's this table that lists, essentially, it's a little bit complicated the way it's printed, but essentially it lists true positive and true negative rates. So percent positive agreement and negative percent agreement, and the corresponding numbers are 93.8% and 96%. So that means if you have been exposed to the disease and your body has produced antibodies for it, then the probability that this test, that the strips in this test will actually show up is 93.8%. That's the true positive rate, and therefore the false positive rate is 1 minus this number. And in the other case, so if you have not been going through this disease, if your body has not produced antibodies, then the probability for this test not to produce all 3 stripes is 96.0%. So that means the false negative rate is 4%, 1 minus 96%. Okay, so these are the numbers, and to a layman like me, these actually sound like a relatively convincing performance for this, so specificity and selectivity for this kind of test. They might convince you that this is actually something important to test at home. And I think a lot of people, partly in the UK, but also all across the world, are looking forward to having such a simple test at home delivered by mail, to put a pinprick on their finger and see whether they are immune or not. Because, of course, this has a massive economic implication as well. So now let's think about what these numbers actually mean. So if a random person uniformly selected from the population actually gets this test delivered by mail to them, and they try this out at home, and let's say the test is actually positive, so all 3 stripes lighten up, then what is the probability that this person actually is immune to the disease? For that I have to go back to my slide. And we just plug in these numbers into Bayes' theorem. So the probability, these are numbers I just quoted to you from the spec sheet. So the probability for a true test, so T being the outcome of the test, given coronavirus infection, C, is 93.8%, and the probability of a negative test, given that we don't have antibodies in our bloodstream, is 0.96. Those are the numbers we can now plug into Bayes' theorem using the formalism we've just constructed. And the question we would like to ask is, given that I get a positive test result, what's the probability that I actually have antibodies, that I'm actually immune to the disease? For that, I just have to plug in Bayes' theorem. So P of C given T, the posterior, is equal to the likelihood times the prior, P of T given C times P of C, divided by the evidence, which consists of 2 possible explanations for this positive observation. So either actually I am immune and then I get a positive result, or I'm actually not immune and this is a false positive. So the probability, we need the probability for this test to be positive given that we don't actually have coronavirus. So this is a number we don't have up here, but it's easily computed using the axiom of complementary probability, if you like, or the result, the theorem of complementary probability, which is that P of T given non-C being probability can be written as 1 minus p of non-t given non-c. Why can we do that? Because conditional probabilities are themselves probabilities, as we saw earlier. And the probability not to have the coronavirus, of course, is just 1 minus the probability to have gone through the infection and be immune to them. So we know many of these numbers now, so we can plug in the true positive rate down here in both places where it shows up, and 1 minus this number up here to get 4%. And the only thing we don't know yet is what's the probability to actually have the virus. So a lot now depends on our probability to have the virus. Well, so of course this is a very debatable, but at the moment I think it's realistic to assume that there's still a very small percentage of the population that has actually gone through the infection. So in Germany, the official numbers at the time that I'm recording this video is that there are the Robert Koch Institute lists about 100,000 cases of coronavirus infections in Germany. Let's assume that that's a massive underreporting and that there are actually 10 times more cases, which might be a realistic assumption. Then that means there's roughly 1 million people in Germany who've gone through this infection, which is about 1%, plus or minus a little bit of the population. So let's say the probability to have this virus is actually 1%. That's because there are about 80 million people in Germany, and 1 million is something like 1% of 80 million, right? Then we can just plug in this number 0.01 into our computation, and that means the posterior probability to actually have immunity, given that you get a positive test, is just barely 20%. For many people, this is a surprising result. I'm sure you, as experts, have seen this kind of computation before, and you're not so surprised by it. But there is a large number of people out there who do not understand this kind of reasoning. And I believe that this test is actually rolled out to an unprepared population. There's a very high probability that a large number of people will believe that they are immune, even though they're actually not. Because of all the people who get a positive test, only about 20% will actually be positive, and all the other remaining 80% will be false positives. So why is this again? And here Bayes' theorem provides us with an explanation of what's going on here. The problem is that in this numerator there are two numbers here that get multiplied with each other, but both of them are actually, so there's one small number that gets multiplied by a large number. So that's the problem, right? So the probability for false positive is relatively small. It's essentially, it's 4%, but it gets multiplied by 1 minus an even smaller number. So the two explanations for this positive result consist of a large number multiplied by a small number plus a small number multiplied by an even larger number. And the two just about, well, actually more than cancel each other out, and we end up with this low probability. So to conclude this lecture, let's take another look at the processes that happen when we as humans do our own internal reasoning with uncertainty, and how they are reflected by this notion of probabilistic reasoning and inference, and also how some of the flaws of our own human reasoning actually show up as well in the probabilistic framework. So let's say you're sitting at home because you're in quarantine, and you're sort of reminiscing a little bit, pondering weak and vary over many a quaint and curious volume of forgotten lore, and suddenly there's a tapping on your door. Now, you might convince yourself that the only possible explanation for this is, 'tis some visitor tapping at my chamber door, only this and nothing more. So there's just a person outside who's knocking on your door, it must be a visitor. Well, let's say that there are many possible visitors you could get at this time of the day. So you might represent these with different variables from V1 to n, how many visitors, how many ever visitors you might actually expect. So let's assume every possible visitor has the same probability of knocking, because that's just what visitors do, right? They show up, they knock on your door. I mean, what else are they going to do if your door is locked from the outside? Then what Bayes' theorem is going to do is it's going to turn out being helpless or useless to you. So if your likelihood is uniform, so if the probability for tapping, given that it's a visitor, is actually the same for all possible terms in the evidence, then you can take that number outside of this sum down here, and it cancels out, and your posterior probability is going to be equal to the prior probability. Which in maybe is not so surprising, because if someone knocks on your door, you don't know who it is, right? So data that has a constant likelihood under all hypotheses doesn't actually provide any information and doesn't change the posterior distribution. This actually happens more often than we'd like, that we end up with likelihoods or kinds of data that are actually not or almost uninformative about the latent quantity we actually care about. But now let's say that there is a special kind of visitor you might be particularly hoping to see again. Maybe some long-lost love interest called Lenore, for which whose loss you're sad about, this rare and radiant maiden whom the angels name Lenore. Then your mind might play all sorts of tricks on you to convince you that this is actually the person tapping at your door. That might happen in various different ways under the probabilistic framework. Actually, in two different ways. Maybe you believe that this particular person, if she would happen to wander past your door, would of course be tapping, because she's that special person and she would never just walk past your door without paying you a visit. So that would mean that your likelihood actually is different for this particular visitor than for all the other ones. Or your brain might convince you that it's much more likely that this person would walk past your door in the first place or come and pay you a visit. So therefore, this special person named Lenore gets a higher prior probability to show up. This is actually the kind of worry that many critics of probabilistic reasoning often mention, that by changing the prior distribution, you can more or less create any possible explanation for the data. If you just convince yourself that this person, Lenore, is so much more likely to visit you than everyone else, then it doesn't really matter what the likelihood is. As long as the likelihood for her tapping isn't zero, you will just always push yourself to believe that this is the person who's currently out there knocking on your door. So maybe then you actually realize that it's the other way around, that you have lost this person, that she's never going to visit you again for reasons that we might not fully understand. Maybe she's dead, maybe she just doesn't like you anymore. Then your prior probability you have to assign to this hypothesis actually is zero. And by convincing yourself that, oh, of course this person is going to come and visit me, you're just going to be wrong. So you have to force yourself to put the prior probability to zero. Only then will you actually maybe get the correct answer, which is that it's very, very unlikely that this special person is knocking at your door. The probability might even be zero if she's actually dead. So by changing the prior distribution, you can actually convince yourself of more or less anything. And that's, of course, something people are often worried about when they think about probabilistic reasoning. In practice, over the course of this term, we will find that often this problem is actually present, but it is much, much more subtle. It's often created not as much by how we distribute truth across the hypothesis space, so what the prior distribution actually is, but the bigger problem is often how we construct this space of hypotheses in the first place. So imagine that actually throw open your door, right? Your soul grows stronger, you don't hesitate no longer, and you open wide the door and find outside darkness there and nothing more. So you've just observed that there isn't any visitor outside, Lenore or else. There's just no one standing outside of your door in the corridor. So the probability for any of these hypotheses is actually zero. Then what this creates is an inconsistency in your reasoning system, because you've just observed that there was a tapping. So the probability for the tapping has to be larger than zero because you observed it, right? And probability theory requires us that the probability assigned to the entire hypothesis space is 1, but we've just decided that all possible hypotheses are 0, so we can't sum up numbers that are all 0 and get back 1, and we also can't compute a conditional distribution given the tapping if there is no explanation in the hypothesis space for the tapping. So the problem here is not probability theory, the problem is how we set up our sigma algebra, or actually even our atomic space of events. So to fix this, and I think this actually happens quite often in human everyday reasoning, when we encounter a surprising result, we have to come up with another explanation for the observation that we previously have considered to be almost impossible. So a philosophical treatment would now maybe say, originally, actually, there were many, many other hypotheses that your brain just pushed down to such a small probability that for reasons of bounds on its own rationality, on its use of resources, you've essentially set to 0. But if we're honest, there is actually a large number of additional hypotheses that we all just for convenience sake assigned a probability of 0 to, but actually we should have assigned a probability of epsilon larger than 0 to them. So maybe you begin to think for yourself, turning back into the chamber, that now you actually hear another tapping maybe. Surely this is something at my window lattice. Let me see then what their at is and this mystery explore. Maybe you've come up with another explanation of what might be, what could be the source of this sound. 'Tis the wind and nothing more. So now you've added one more possible hypothesis. And because we've done that at a later point, of course our previous reasoning had to be flawed because this hypothesis was never part of our reasoning process to begin with. This is going to be a very frequent problem in our inference process, that we have to write down the correct variables before we even begin reasoning, because otherwise all of our results could be flawed, no matter what the prior distribution is. Now, of course, those of you who've seen this poem before know that even this hypothesis is actually wrong. So now, as you open your door, in comes, with many flirt and flutter, a stately raven of the saintly days of yore, and flies in and lands on the pallid bust of Pallas just above your chamber door, and perches and sits and nothing more. So if your hypothesis space just never includes the right correct explanation to begin with, then probability theory cannot help you at all. It will always assign 0 probability to the correct hypothesis. This is a big worry, of course. That's the most fundamental worry anyone could have about any reasoning system. Unfortunately, this problem, of course, has nothing to do with the mechanism of probabilistic reasoning. It has to do with the set theoretic part of probabilistic reasoning, which is that you have to set up your space of hypotheses before you even begin reasoning. Okay. Another simple way to phrase this is a famous quote by one of the fathers of probability theory. Actually, I will mention this name maybe more often than Kolmogorov. He was around long before Kolmogorov, the French mathematician Pierre-Simon de Laplace, who lived in the 18th and 19th century, and he provided some of the basic formalisms for probabilistic reasoning before there was a set theoretic formulation for them. He seems to have been an extremely intelligent chap, and one of his famous quotes, among many, is that probability theory is nothing but common sense reduced to calculation. These examples I just showed you hopefully highlight this issue, that it's down to you to define your hypothesis space and to assign prior probabilities to all the latent variables, but also to provide a likelihood function that provides a conditional probability for any possible observation given the hypotheses. Both, or actually all three of these objects, the hypothesis space, so the sigma algebra, and the joint probability measure over all of these variables, are part of what you have to design when you build your own reasoning system. And the pitfalls which you will encounter in the use of probability theory will typically, well, they will never arise from the use of Bayes' theorem. They will always arise from these kind of flaws. That there are explanations that we have not considered, or that there are mechanisms at play in the likelihood that we have not considered in constructing our reasoning system. But there will be time, enough of it, over the entire semester to think about this issue. So with that, I'm at the end of the content part of the lecture. I also want to very briefly use this opportunity to bring in two pieces of technical information or administrative information for those of you taking this course and not just watching for fun on YouTube. We will begin the interactive part of this lecture with a flipped classroom on Tuesday, the 21st of April from 10:15 to 12 o'clock. We will try and do this once every week, every Tuesday at this time slot. This will be an opportunity for you to ask me questions. We will also use the other time slot originally assigned to this lecture to do exercises. I'll say something about this in a moment. To get into this flipped classroom, we need some form of entrance control, some identification. And to do that, we will provide credentials to all signed up Tübingen students who sign up in Ilias. To do that, you have to, of course, have an account on Ilias. If you don't have one and you think that you should be allowed to take this course because you're a qualified student in Tübingen, then please send me an email. You can find my email address on our website. If you already have an Ilias account, then of course you can sign up yourself by going to my teaching webpage, and there is a link where you can directly sign yourself up on Ilias. Many of you have already done so. I'm looking forward to hear more from you. Another thing that you might know if you've seen some of my lectures before is that I collect instant feedback on every single lecture that I give. Usually I do this with pieces of paper that people fill out. Obviously that's not going to work this term. So instead there will be a poll on Ilias for this lecture and another one, the next one, and for every other lecture following it. I hope that you fill out this form. Please do so. Otherwise I have even less feedback about what you think about this course than I would usually have, because I really can't see your faces. I don't even hear you moan if I say something stupid. Okay? The other thing I should briefly say is that there are, of course, exercises associated with this course, which you have to take for credit. I will say more about how the exercise system is going to work, how tutorials are going to work in the flipped classroom. But maybe it suffices to say, as an advance notice, that there will be a plenary, symmetric, hopefully, if it works out, plenary tutorial every Monday from 10 CT to 12, so 10:15 to 12. This course comes with a number of exercises. There will be basic exercises, there will be mathematical, relatively simple theoretical exercises, and then every week there will be a programming exercise that goes alongside the course and gives you an opportunity to really try your hands on these mechanisms and algorithms and models and tools that we're going to encounter over the course of this term. And they will quickly become much more hands-on. As a startup exercise this week, we've given you something that I think is actually really important in this phase of the development of machine learning, which is an opportunity to test for yourself how useful the deep learning, the standard tool that many people now think of as machine learning, actually is for generic data sets. So many of you might think, having taken a deep learning course last year, that all of machine learning is deep learning, and if not, then all of old machine learning is now outdated and everything should be deep learning. We should try whether that's actually true or not by this week's exercise, which I'm not going to read out, but it basically works as this. Here's a data set. Many of you will have seen this before. It's the famous Keeling curve of CO2 concentration in the atmosphere collected over the Mauna Loa volcano on Hawaii. And your task will be this week to use any standard deep learning toolbox you like and use it to construct a prediction of this data set into the future. And I'm very much looking forward to see the result of this modeling task, what you come up with. While you do that, maybe pay attention to a few interesting questions. One of which is, how easy is it to set up your model? So I'm actually hopeful that some of you will come up with quite interesting deep learning models. How much knowledge do you think it takes to build these kind of models? Later in the course, we will encounter probabilistic models that allow us to do the same thing, and we have to compare how hard these models are to build manually. Think for yourself how much you trust this model. That has something to do with how much you understand it and whether you think it's the right model or not. And think for yourself about the uncertainty that this model might be associated with for you. So that means how much do you actually trust this model. With that, I'm at the end of the lecture. I have tried and used these first few minutes that we have together this term to introduce you to the notion of uncertainty, point out that uncertainty is a fundamental part of our daily lives, of scientific, medical, and societal processes, even political processes, and that being able to deal with uncertainty is one of the most important parts of human intelligence. To address this, we constructed a formal reasoning system called probability theory, purely from a relatively basic axiomatic system, which is based only on the distribution of a finite amount of truth across sets of sets. And we noticed that there is actually very little philosophical motivation we have to provide for the system. We only have to assume that we have a certain space of hypotheses over which we distribute a finite amount of truth, and then we just have to make sure that when we construct sets of subsets of this space, that we add up probability in the correct way so that we don't accidentally add additional probability so that it doesn't sum to 1 anymore, or lose some probability in the process so that it doesn't sum to 1 anymore. In doing so, we also arrived at two elementary rules of probability theory, the sum rule and the product rule. These are stated here again. Actually, the product rule wasn't so much an axiom, it wasn't so much a theorem as an axiom, it was actually a definition. I pointed out that there are also philosophical ways of motivating this choice of the definition of the conditional distribution. Well, we didn't do them today, just to save some time. These two together give an almost immediate corollary, which is known as Bayes' theorem, and Bayes' theorem provides the mechanism for reasoning under uncertainty by giving a relationship between posterior probability for a hypothesis given some observed data and a prior probability and the likelihood to observe this data if this particular hypothesis is actually true, by normalizing it with the probability, the so-called marginal probability for this data, which arises by just summing out all possible such explanations for the data under various hypotheses. We notice that this framework allows us to formalize simple reasoning processes, even those that might be quite important at this point in time for our society. And we also saw that this process, this mechanistic process, does not absolve us, the designers of algorithms, from the responsibility to actually put the right assumptions into our model. And this doesn't just amount to distributing prior probability. Actually, distributing prior probability is often the easiest part of this process. The much more crucial aspect is that the hypothesis space has to be the right one, and that likelihoods have to actually faithfully capture relationships between latent variables. I hope you've enjoyed this lecture, and that I'll see more of you. Actually, you will see more of me in the coming months. Thank you very much for your attention.